We all kind of take clean, safe drinking water for granted. You turn on the tap, and there it is. But the science that makes that happen is this incredibly delicate dance. And today we're diving into some new research that throws a totally unexpected wrench into the whole process.
Okay, so think about it. Basic chemistry, right? Heat usually makes chemical reactions go faster, makes things easier. So it just makes sense that cleaning warm water would be more efficient. But what if it isn't? What if the complete opposite is true? What if water actually gets harder to clean the hotter it gets? That's the bizarre puzzle we're tackling today.
All right, to get our heads around this, we first need to meet the main villain of our story. Its name is turbidity. It's just the scientific term for cloudy water. And believe me, fighting it is one of the biggest jobs for any water treatment facility.
So what is turbidity, really? Well, it's basically just countless tiny, tiny particles floating around in the water. We're talking microscopic bits of clay, silt, organic gunk, stuff that's so small and lightweight it just won't settle down on its own. It just hangs there, making the water look murky and, well, pretty gross.
And this isn't just about the water looking bad. Oh no, this cloudiness is a real problem. For one, it jacks up the cost of treatment because you need more chemicals, and it's constantly clogging up filters. But way more important, these little particles are the perfect hiding spot for dangerous germs, shielding them from disinfectants. They can even create nasty new chemicals when they mix.
So how do we actually fight back against all this turbidity? Well, for over a century, the go-to method has been this really clever three-step process. The whole idea is to trick these stubborn little particles into doing the one thing they refuse to do on their own, sink to the bottom. And our hero process has a bit of a mouthful of a name: coagulation, flocculation, sedimentation. Yeah, let's just call it CFS for short, okay? This is the gold standard. It's used in water treatment plants pretty much everywhere. So here's how the magic happens. First up is coagulation. You add chemicals that basically zap the electrical charge that's keeping all those tiny particles apart. Then comes flocculation. The water is stirred really gently, which encourages all those neutralized particles to start clumping together, kind of like they're holding hands, to form these bigger, heavier chunks we call flocks. And finally, sedimentation. You just stop stirring, and all those heavy flocks, they sink right to the bottom, leaving beautiful, clear water up top. Now, you might be wondering, how do scientists figure out the perfect recipe for a particular water source? Well, in the lab, they do this thing called a jar test. It's basically a miniature version of the whole CFS process. They can mess with the amount of chemicals, the mixing speed, everything, until they find the absolute best, most efficient way to get that water clean. Okay, so now we get to the heart of it. We've got the basics down of how we clean water, so let's bring in that wild card, that unexpected variable that just throws a huge wrench in the works: temperature. I mean, everything we know about chemistry says this should be a slam dunk in warm water, right? Particles are zipping around faster, reactions happen quicker. It should be easier. But when the researchers actually put this idea to the test, the data told a completely different story. Let's just look at the proof. These two graphs are key. The one on the left shows how much chemical they had to add at different temperatures. And you can see it. The dose actually goes up as the water gets hotter. And then look at the graph on the right. Even with all those extra chemicals, the water at the end is still cloudier when it's hot. It makes no sense. This really just spells it out for us. Look, in really cold water just above freezing, you use a smaller dose of chemicals, and boom, you get rid of 83% of the cloudiness. Fantastic. But in hot water, you have to use more chemicals, and you only get a 78% removal rate. You're literally paying more for a worse result. It gets less efficient as it heats up. So what is going on here? Well, the researchers themselves have a theory. They think that at those higher temperatures, the clumps themselves, the flocks, are actually changing. Maybe they get bigger but fluffier so they don't sink as well, or maybe brand new tiny particles are forming that just refuse to settle. The heat is literally changing the physics of the whole process. All right, so we've got this very real temperature problem. But is there a way to fix it? Is there a workaround? Researchers tested a really cool technique. They thought, what if we could kind of seed the process to give it a little head start? The technique is called sludge recycling, and it is exactly what it sounds like. You take the gunk, the sludge, that settled out from the last successful batch, and you add a little bit of it back into the brand new batch of cloudy water. The idea is that these old, settled particles act like a perfect foundation for all the new clumps to grab onto and grow. And in cold water, oh, it works like a dream. Check out this chart. The first bar, with no sludge, the cloudiness is at about 20. Then you add just a little bit of sludge and it gets cut in half. Add some more and it gets even clearer. So in the cold, it's simple. More sludge is better. But now, look what happens in the hot water. Okay, adding a little sludge still helps. You can see that big drop. But then, when they add more sludge, the water actually gets worse again. It gets cloudier. In hot water, too much of a good thing is actually a bad thing. And that right there, that is the crucial takeaway from this whole thing. There is no one-size-fits-all magic recipe for cleaning water. The absolute best way to do it, how many chemicals you use, whether you recycle sludge, how much sludge you use, it all changes. And it changes dramatically based on the temperature. So why does all this matter? I mean, who cares about some scientists playing with jars of cloudy water? Well, we all should, because the challenges they were simulating in that lab are the exact same ones that real-world water treatment plants have to deal with every single day. This has huge real-world implications. Think about it. The river or lake where your town gets its water isn't the same temperature all year round. So a treatment plan that works perfectly in the dead of winter could be a complete disaster in the middle of summer. These plants have to be constantly adjusting their recipe to match the conditions outside. So, what have we learned? Well, for one, that cleaning our water is way more complex than dynamic science than most of us ever imagined. 2, temperature isn't just a small factor, it's a critical and totally counterintuitive variable. And finally, this shows us that even our smartest solutions like sludge recycling need to be constantly tweaked and adapted. And that's exactly why this kind of research is so vital. And that leaves us with one last pretty big question. We've just seen pretty clearly that hotter water is harder and more expensive to clean. So as our planet continues to warm up and our water sources get warmer too, this challenge is only going to get bigger. The real question is, how are we going to innovate to keep up?